record? No. So welcome everyone to Tokenomics 2021. My name is Hannah Halpern. I'm a professor at NYU, and I wish I could welcome you in person at NYU. Unfortunately, we are still stuck with Zoom meetings. I hope we will make the most out of it, and also take advantage of the fact that Zoom allows us to connect geographically much more easily. So this is a third edition of Tokenomics conference after Paris in 2019 and supposedly Toulouse in 2020, but also ended up to be on Zoom. This is an interdisciplinary conference connecting people from different fields, including computer science, economics, finance, information systems, who share the interest in blockchain and crypto topics. Now, the different disciplines have different approaches and different methods and different focus on questions, and this should be a source of inspiration. But often, what we end up with, listening to a talk, directly listening to a talk from a different field, is that we really miss the significance. So because of that, this year, for this edition of Tokenomics, we asked the session chairs to do more than just time keep and facilitate questions and answers. We asked them to provide a short introduction to why the topic in their session is a significant topic, and what are the questions around this topic. This should help to frame the individual talks in the session, and I want to thank the session chairs for taking on this additional role. Also, in the breaks after each session, we will have breakout rooms so that the discussion about each paper can continue. So there will be a breakout room for each paper in the session where the authors are going to join, and anyone else who would like to discuss is welcome to join as well. So with that, let's start. We have a great lineup for today and for tomorrow, and we start. I wanted to start with a bang, and this is why we're starting with Joe Halpern's keynote, and he will be introduced by Raphael. Please take it on, Raphael.
Thank you, Hannah. Can you all hear me?
Yes. Yes.
So it's my very great pleasure to introduce our first invited speaker to the conference, and that is Joe Halpern. Joe is actually a very close friend of mine and a collaborator for a long time, and it's especially fitting actually to have Joe start off this conference, as many years ago Joe himself started a conference that's called TARC, which has some of the same high-level goals as this conference, namely bringing together economists and computer scientists under a common roof. And we're really striving to do the same here. Indeed, Joe actually is really one of the pioneers in bringing the fields of economics and computer science closer together. And many of his works have truly been seminal in shaping these connections between the fields. These include celebrated works on reasoning about knowledge, reasoning about uncertainty and causality, which are now classics in both computer science and economics literature. Joe has won lots and lots of awards, too many of them for me to list here, but let me just mention some of the greatest awards in computer science, including the Gödel Prize, the Dijkstra Prize, the ACM Newell Award, and many, many more. He's also won lots of Best Paper Awards and is, among other things, also an elected member of the American Academy of Arts and Science and the National Academy of Engineering. And these are some of the highest distinctions one can get in science and engineering. Let me finally mention that Joe is not just a great scientist, he's also one of the wisest and kindest people that I know. Personally, for me, Joe is not only a role model for what it means to be a great scientist, but also what it means to just be a great human being. He's a fantastic mentor for students, junior faculty, and even senior faculty. So with that, I'm really excited to let Joe tell us about one of his more recent celebrated connections between economics and computer science. And this is in how to bridge the worlds of distributed computing and game theory. So please join me in welcoming Joe.
Wow, thank you, Raphael. I hope I can live up to that introduction. So I don't know how you're doing it in terms of questions. I would be happy to entertain questions during the talk if they're short. So and then longer questions can maybe wait to the end, but don't hesitate to ask a question if you have one. So this is really, some of the work is not so recent. It's joint work with Danny Dolev, Itai Abraham, and Enrique Gonen on combining distributed computing and game theory. And then I'll also talk about some quite recent work with my former student, Ivan Geffner, who just graduated. So here's the picture, and I'll try to do everything from scratch, but there are really two views of the world. I'm going to call one the computer science view, distributed computing, cryptography. And there, the view had always been that agents are either good or bad. Good agents do what they're supposed to do. They follow the protocol. Bad agents do all they can to subvert it. So we have things like Byzantine Agreement, where we have malicious agents whose goal, if you like, is to subvert the protocol. And this made a lot of sense from the computer science perspective, because the original motivation was, you imagine a system designer writing a protocol, but you might have some computers being flaky and not doing what they're supposed to do. And we want to tolerate the case where where they seem to be malicious. But the original picture wasn't that they were malicious, but we just know that when something goes wrong, sometimes it's the worst thing that goes wrong. So if we can prove that our protocol does good things despite the fact that we have malicious computers who are trying to subvert it, then we can have a lot of confidence in the protocol. So that was the CS point of view with malicious agents, and where everybody's either good or bad. And again, the good ones, without thinking, would just follow the protocol. Now, game theory assumes that all agents are rational and they try to maximize their utility. There's no notion of good guys and bad guys. There's no moral judgments here. If you're trying to maximize your utility, that's perfectly reasonable. If you can do better by not following the protocol, then that's okay. And that certainly makes sense in a lot of contexts. And our goal was to combine these viewpoints, because we claimed that the combined viewpoint made a lot of sense for computer science. So as I said, Byzantine Agreement is the paradigmatic example in distributed computing, and I'm sure all the computer scientists know what Byzantine Agreement is, but in case there's some economists who don't, let me just briefly review the standard story. Their end soldiers, up to T of them may be faulty. N and T are assumed to be common knowledge, so everybody knows, an upper bound in the number of faulty agents. Now, each agent starts with an initial preference, which you can think of as either 0 or 1, either attack or retreat. And we want an algorithm that guarantees that all the non-faulty soldiers do the same thing at the same time. So there's an implicit assumption of synchrony here. And if all the soldiers are non-faulty and their initial preferences are identical, that's what they do. So let me explain the second point. So we have an algorithm. We can't say anything about what the faulty ones are doing. So we're assuming that all the non-faulty ones follow the algorithm. And if they do, then they'll all attack or they'll all retreat. Again, we can't say anything about what the faulty ones are going to do. That's the assumption. Now, there's a trivial algorithm for this, which is attack no matter what. Or another trivial algorithm is retreat no matter what. So the second condition is really meant to preclude the trivial algorithm. It says if all the soldiers are non-faulty and their initial preferences are identical, then they have to do that. So you can't attack no matter what, because if everybody initially wanted to retreat and they were all non-faulty, then you're supposed to retreat. Okay, so that's the story in Byzantine Agreement, and algorithms were developed for Byzantine Agreement, or all sorts of the whole cottage industry in Byzantine Agreement. So people looked at different kinds of failures. Byzantine failures are where soldiers can lie and cheat and steal, and then agreement is possible if 3T is less than N. So the upper bound of the number of failures is less than a third of the total number of agents. So N is the total number of agents. T again is the upper bound on the number of agents who could be faulty. Doesn't mean they all are necessarily T faulty ones, but it's an upper bound. Now, if you limit to crash failures are failures where you might crash in the middle of sending a message, but you're not going to lie. And once you've crashed, you stay crashed. So it's shown that with the Byzantine failures in cryptography, messages signed with unforgeable signatures, agreement is always possible. With crash failures, agreement is always possible. And agreement, when it's possible, is reachable in T+1 rounds. And in fact, T+1 rounds are required even if no soldiers are faulty. All start with the same initial preferences. Only crash failures are possible. So even in the most, if you like, benign case, where in fact nobody's faulty, and and we know if they're going to be faulty at all, they're just going to crash. And even if they all start with the same initial preference, you're going to need T+1 rounds. So these results are relevant because I think the work on Byzantine Agreement motivated a lot of the work on blockchain. And blockchain can be viewed as an attempt, again, to coordinate. You can think of Byzantine Agreement as an attempt to get the good guys to coordinate, all do the same thing. And there's a sense in which in blockchain, we're coordinating on what's on the blockchain. We're all sort of agreeing on what's the blockchain. So now from a game theorist perspective, Byzantine Agreement is a game between two teams of unknown composition. It's a game between the good guys and the bad guys, except you don't know up front who the bad guys are going to be. So that's the first thread that I want to talk about, is fault tolerance. Now put that on the stack. I want to bring in the second thread into the story, which is multi-party computation. So multi-party computation goes back a long way. Andy Yao actually won a Turing Award largely for his work on multi-party computation. There's a very significant paper by Goldreich, Mihaly, and Vigdorson. So it's a paradigmatic problem of cryptography. The picture is each agent has a secret input, and they want to compute some function of that input without revealing any information other than the function's output. So you can imagine we want to compute a majority value. The inputs are all zeros and ones. The function might be compute the majority. Or if the inputs are salaries, the function might be compute what the highest salary is, or maybe even compute who has the highest salary. So it's some function of the inputs. You get to know the output of the function, but you don't know, intuitively, you don't know any information besides that. So a little bit, still intuitive, but a little bit closer to the formal definition. We can imagine that a trusted third party, I'm going to call that the mediator, had computed the function. So if each agent sends the trusted mediator their value, the trusted mediator computes the value and announces the value. And intuitively, now you don't know anything but the output. So if you can sort of simulate the trusted mediator, you've done multi-party computation. And again, there are protocols for multi-party computation. And the picture here was the same as the picture in Byzantine Agreement, that there was a certain number of bad agents. So all the good agents followed the protocol. The bad agents could do whatever they wanted. And again, the protocols work depending on where the number of bad agents fewer than a third of the total number, or fewer than a half the total number, and that depends on the underlying assumptions. I won't go into details here, but again, there's a rather large literature on multi-party computation, and you can see the overlap with the literature on Byzantine Agreement, because again, the picture is there are good guys and bad guys. The good guys follow the protocol, and the bad guys can do whatever they want, or maybe not just whatever they want. It depends on the underlying assumptions. Now, let me come back to mediators. Mediators, I claim, are of interest beyond just multi-party computation. Imagine we have an auction where people don't want to bid publicly, right? So they have these auctions, for example, for the rights to drill for oil. Well, maybe that won't happen in the future, but not too long ago, companies like Exxon and Chevron and BP were competing for the right to drill offshore. And there was an auction, so you bid for the right to be able to drill in a certain tract of land. Now, you might not have wanted other companies to know what your bid is, because you've had your geologists inspect the tract, and if you think it's a very valuable tract, you bid high. That's giving other companies information. They know maybe they haven't inspected the tract, but they know that your geologists have, and if you're bidding high, that tells them something without even bothering to send their geologists out there. So companies did not want their bids to be public. And of course, you could do this if there were a trusted third party. Each agent submits their bid to the trusted third party, and the trusted third party announces who wins the auction, but doesn't announce the bids. And likewise, by the way, going back to the first thread, Byzantine Agreement can be solved really easily with a trusted third party. Each player tells the mediator his preference, and the mediator chooses the majority. So as long as n is greater than 2t, as long as the number of bad agents is fewer than a half the total number, so for sure, if everybody is non-faulty and has the same preference, then they're all going to say the same thing to the mediator. Mediator will choose the majority, so they'll do what everybody wants to do. And if the players do what the mediator tells them to do, they'll all do the same thing. So we'll have solved Byzantine Agreement, no problem. So basically, in the rest of this talk, so implementing mediators is a paradigmatic problem in game theory, as well as computer science. And this was the amazing thing to me and my collaborators when we first started looking at this literature. So let me focus on the dates. Yao, 82, Goldreich, Macaulay, Vigdorson, 87. So try to say, as the computer scientists in the audience will know, these people are extremely prominent people in computer science. Andy Yao won a Turing Award. Sylvia Macaulay won a Turing Award. Avi Vigdorson just got the Nevin Luna Prize and the Abel Prize in mathematics. Oded Goldreich has won many prizes, the Israel Prize and many others. These are extremely prominent people. Now look at the dates and the economists. Roger Myerson, 1986, also won a Nobel Prize. Francois Forge didn't win the Nobel Prize, but is also an extremely prominent economist. So economists were working on implementing mediators in the late 80s, just like computer scientists were. And I claim if you stand back a few yards or a few meters, depending on where you're from, they were doing more or less the same thing. They were saying, here's a problem we can solve with the mediator, with a trusted third party. And the question is, can we get rid of the trusted third party? Right? So we know how to solve the problem if we have a trusted third party. It's easy. We all tell the trusted third party what we want to do. The trusted third party announces what you should do. You can listen to him or not. In the game theoretic sense, you don't have to listen to the mediator, but it turns out to be an equilibrium to do so. So the question was, if you can do something with a mediator, can you do the same thing? And I'll put same thing in quotes here, because what that meant wasn't exactly the same in the two literatures. Can you do it without the mediator? So in the economic literature, the way they worded this, can you achieve the same result with cheap talk? Players talking to each other, perhaps promising each other what they're going to do. Oh, I promise, I'll do this if you do that. But it's cheap talk because there's no way you can force, it's an empty promise, right? If I don't do what I promised I would do, there's no way you can force me to do it. It's not like there's a judge who can force me to do it. So what's the difference between the literatures? So in the game theory literature, they talked about Nash equilibrium, and they assumed, well, if you can achieve a Nash equilibrium with the mediator, can you achieve the same equilibrium, and I'll make that precise, just using cheap talk, just with the players talking to each other without a mediator? And this is really close to what people were doing in the cryptography community. If you can do something with a mediator, can you do the same thing without a mediator? Now, what's the difference? Well, and of course, in the game theory literature, there was an emphasis on rational players. This was Nash equilibrium, that achieving the same thing meant you got the same outcome and nobody could gain by deviating. It's an equilibrium. It's a Nash equilibrium. There was no notion of faulty players who were doing whatever they wanted. There were no concerns officially about privacy in the game theory literature, although typically the solutions provided privacy, interestingly enough, although it wasn't part of the definition of what was desired. So basically, in the rest of this talk, I want to combine these threads, bring together ideas from game theory and distributed computing. So the first step is we wanted to talk about K-resilient equilibria. So Nash equilibrium tolerates deviations by one player. It's perfectly consistent with the Nash equilibrium that two players could do better by deviating, right? So if Raphael and I got together, and we colluded, and we both did something different, we might have a Nash equilibrium, but it's perfectly consistent. That Raphael and I could deviate and get a better outcome. So here's a simple example. So we defined a notion of K-resilient equilibrium if no group of size K can gain by deviating. And why do we care about K? Because we thought, realistically, you might be able to get a coalition of 3 or a coalition of 4 to work together. It's awfully hard to coordinate a coalition of 100. So we took K as a parameter, but we were mainly interested in K being relatively small. So here's an example. Suppose we have a game where everybody has to play either 0 or 1. If everybody plays 0, if they coordinate on 0, they get the payoff of 1. If exactly 2 players play 1 and everybody else plays 0, then those 2 players get 2 and the rest get 0. And otherwise everybody gets 0. Now everybody playing 0 is a Nash equilibrium, because if everybody plays 0, everybody gets 1. And if one person deviates, the only way you can deviate is to play 1, then you're in this third clause, right? The only way you get a different payoff of 2 is if 2 people deviate. So everybody playing 0 is a Nash equilibrium, but it's not too resilient. If Raphael and I got together and agreed that we were both going to play 1, then we would get 2. The rest of you get 0. I don't care about that, but we could do better by deviating. So I hope that makes sense, that this is an equilibrium that tolerates deviations by 1 player. It does not tolerate deviations by coalitions of, in this case, 2 players.
Is there too resilient equilibrium then? I mean, that's sort of the beauty of Nash, right? That we can prove existence. Maybe there's one in mixed strategies? Or?
Sorry, one more time.
Well, is there an equilibrium, or actually that's too resilient?
In general, no.
In this game here, so I see. So that's interesting.
So one of the nice things that economists like about Nash equilibrium is that Nash proved, that was his thesis for which he ultimately got the Nobel Prize, the Nash equilibrium always exists, at least if you allow randomized strategies. It is not in general the case that K-resilient equilibria exists for K greater than 1. You can come up with counterexamples. So I should say historically, Bob Aumann, who also got a Nobel Prize, had already considered resilient equilibrium back in 1959. He only considered K-resilient equilibrium for all K. He called that strong equilibrium. So he wasn't particularly interested in coalitions of size K, but the notion of resilience was something that he was certainly aware of back in 1959. Interestingly, there's very little work on resilient. I mean, so there was some follow-up on Aumann's work, but very little. And my conjecture sociologically is that economists weren't interested in it precisely because in general, they didn't exist. So I mean, it seems as a cultural phenomenon that economists are only interested in equilibrium notions when they exist, partly because they're viewing these equilibrium notions as predictions as to how the game will be played. And if there are games where the equilibrium doesn't exist, what are you going to predict, right? So that's my guess, but certainly it's an empirical fact that there was very, very little work in the econ literature on resilience, despite the fact that Aumann already introduced it in '59. So that was one thing we wanted. We wanted to carry resilience, but I claim that's not enough. So here I want to, again, borrow ideas from the Byzantine Agreement literature. So the assumption with K-resilience is these are rational agents. And of course, they're going to deviate because they're better off by deviating. At least if I can convince Raphael to deviate together, if we can do a coordinated deviation, we're going to deviate because we're better off by deviating. We're perfectly rational in deviating. But it seems reasonable in some settings to imagine that agents don't respond to incentives, or at least they don't respond to what you think are the incentives. Maybe that's because their utilities are not what we thought they were, right? I mean, we had people flying planes into the World Trade Center and blowing themselves up, and you could say they're irrational. Why would you do that? Well, I mean, a reasonable comeback is that they just had different incentives than you had. They were being perfectly rational. They just had a different utility function. So one explanation of agents not responding to incentives is that you don't understand their utility function. But in the computer science literature, we want robustness, because suppose I have a faulty computer. So apparently I'm not responding to incentives. I'm not doing the right thing. It's not because I'm irrational. I would love to do the right thing. but my computer is flaky and I can't. Or imagine my mother on the internet. I mean, she'd love to do the right thing, but she's just not very good with computers. So she's doing the wrong thing, not because she's irrational, but because she's not very good on a computer. So to ignore agents like that seems like a bad idea, right? So I claim what we would like, the standard work in computer science, but is robustness, that we want an equilibrium that's robust in the sense that it allows for some agents who, for whatever reason, are behaving in a way that doesn't make sense to you. And, such apparently irrational behavior is not uncommon. People share on Pirate Bay and BitTorrent. I mean, it costs them some bandwidth, but they're willing to share files, maybe even at the risk of being sued. So I want to distinguish this notion of robustness, where we allow for irrational players, from resilience. So one more example. So consider a group of end bargaining agents, and they have two options. Either they stay and bargain, in which case they all get 2, or they can go home. Now, I'm going to tell you, anybody who goes home gets a payoff of 1. If everybody stays and bargains, they all get a payoff of 2. But if some people stay while other people are going home, the people who stay get 0 if not everybody stays. So if I stay but Raphael goes home, Raphael gets 1 because anybody who goes home gets 1. But I stayed and not everybody stayed, so I get 0. The only way we get 2 is if everybody stays. Okay. Now I claim this game has 2 equilibria. So if you think about it a little bit, I would normally ask, wait for the audience to figure it out, but maybe this time I will just tell you, and I hope it's obvious. Everybody going home is an equilibrium, a Nash equilibrium, that is. Everybody staying is a Nash equilibrium. Clearly, if everybody stays, nobody has any incentive to go home. They get 2 by staying, they get 1 if they go home, right? Clearly, if everybody goes home, nobody has any incentive to deviate. There's no point in staying. I'm going to get 0, right? So I hope it's clear that everybody staying is an equilibrium, everybody going home is an equilibrium. And clearly, the equilibrium where everybody stays, Pareto dominates the equilibrium where everybody goes home. On the other hand, if you were in this situation and think of n as being 1,000, what would you do? Right? So I don't know about you, but if it were me, I would go home. Right? Because going home, I'm guaranteed to get 1. And if I stay and there's 1,000 people out there, I'm always worried that one person, for whatever reason, won't stay. Right? Maybe somebody has a sick kid and needs to go home. Or maybe somebody's sick and needs to go home, right? I mean, I don't trust everybody else to stay. Going home intuitively is a robust situation. That I get 1 no matter what. Staying is a rather fragile equilibrium because it gets broken as soon as anybody gets home. Does that make sense? So I want to take, I want to consider equilibria that are robust in the sense that they allow for a certain number of, if you like, irrational players. And I claim people certainly take such possibilities into account. So the question we're going to look at, bringing back mediators, as I said, I'm going to tie together these threads. Can a KT robust equilibrium be obtained? If you can obtain a KT robust equilibrium with a mediator, can you obtain it using cheap talk? So now I'm using economics speak, but if you can do something with a mediator, can you do it without? Now notice here I'm combining ideas. So let me make this a little bit precise. So a protocol is T-immune if the payoffs of the good agents are not affected by the actions of up to T other agents. So this is a robustness property. Again, if you think of this example, going home is T-immune for arbitrary T. My payoff, which is 1 if I go home, is not affected by what anybody does, right? On the other hand, if I stay and bargain, my payoff is very much affected by what other people do, because I have to count everybody staying to get my payoff of 2. So I'm going to say a protocol is T-immune if the payoffs of the good agents, the ones who follow the protocol, aren't affected by the actions of up to T other agents. So think of this as a robustness property. It says, up to T other agents, whatever they do, it can't hurt me. So I'm going to be interested in what we call KT robust equilibria. KT robust says it's a protocol that tolerates coalitions of size K. So K agents can't gain by, up to K agents can't gain by deviating, and is T immune, which means that my payoff can't be hurt by up to T agents. So you can think of Nash equilibrium as a special case where K is 1 and T is 0. It's 1-0 robustness. And in general, KT robust equilibria don't exist, which again is part of why I suspect economists haven't looked at them that carefully, but they can be obtained with the help of a mediator. So the question we're going to be asking is, if you can get it with a mediator, can you implement it with cheap talk? But let me just stop for a second and point out how we're really combining ideas from game theory and computer science. That these coalitions of size K, we're going to have utilities, and it's K robust to say tolerates coalitions of size K. I'm going to say that a coalition of size up to K can't gain by deviating. So this is just like Nash equilibrium. If with K equals 1, you don't do better in terms of utility by switching to a different strategy, even if you can get a bunch of other people to deviate along with you. The immunity is more like Byzantine Agreement. This is saying that I don't care what the bad guys do. They can lie and cheat and steal. I'm still going to get my good payoff, right? So that think of the T as 0T is more or less like Byzantine Agreement, being able to get my payoff no matter what T people do. And the K, well, when K is 1, it's Nash equilibrium. So I hope that makes some sense. So let me give you a flavor of the kinds of results we get. That says, again, we're saying if you can do something with a trusted third party, with a mediator, can you do it without? So let me actually stop and let me make this a little bit formal, just to make sure we're all on the same page. So technically, we really are considering 3 different games. There's what we call the underlying game, where players, it's a simultaneous move game, where there's a payoff matrix. So it's a one-shot game in normal form. Everybody makes a move and gets a payoff. That's the underlying game. Then there's the game with the mediator. That's an extensive form game, because the players are communicating with the mediator back and forth. They can communicate. And at some point, they make a move in the underlying game. Their payoffs are the payoffs in the underlying game. After everybody's made a move in the underlying game, and in the synchronous case, you can assume that that move is made at the same time. I'm going to come back to the more general asynchronous case. But once the move is made, now they've all made a move. And as I said, the moves are the same moves as in the underlying game. They get a payoff, and the payoff is just the same payoff as in the underlying game. It's the underlying game that determines the payoff. So game 1 is the underlying game. Game 2 is the game with the mediator. Game 3 is what we call the communication game. Or actually, it's been called the econ literature, the communication game. That's where there's no mediator. Their players are just talking to each other. So again, now the picture is they're talking to each other. At the end of the day, they make a move in the underlying game, and their payoffs are the payoffs in the underlying game. So in all 3 games, there's the same set of ultimate moves, but of course, in the game with the mediator and the communication game, another kind of move is communication. I can talk to you, I can send you a message, right? But once you make a move in the underlying game, well, once everybody has, then the game is over and the payoffs are just the same as in the underlying game. So to say that a communication game implements a game with a mediator, it's saying that, well, if you had a KT robust equilibrium with the mediator, so with the mediator, you had strategies that could tolerate deviations of up to K players. K players couldn't do better by deviating, and tolerate arbitrary moves by up to T players. Tolerate, in this case, means and your payoff is not affected. Even, by the way, in the formal definition, if the K players collaborate with the T players, if the if the colluding players of size K can collaborate with the T players who are acting arbitrarily, they don't gain by deviating, and the T players can't affect your payoff. And the question is, if you could get one of these KT robust equilibria using a mediator, can you get rid of the mediator? And just do it by talking to each other. And the answer is yes, if n is sufficiently large. So this isn't the spirit of the results of Byzantine Agreement. Remember, the Byzantine Agreement results said you could do Byzantine Agreement if n is greater than 3t. Well, here we can do it if n is greater than 3 times k plus t. Remember, these k and t are parameters. And you can do it even if you don't know the exact utilities of the other players. And the protocol runs in bounded time. And you can even assume, if in a synchronous system, that the protocol runs, and then simultaneously you're all making a move in the underlying game and getting your payoff. Now, it's interesting, in the econ literature, there were results on being able to implement Nash Equilibria. So if you could get a Nash equilibrium with a mediator, could you do it without? And this is a result that goes back to Barney in 1989, a Hungarian mathematician. And the result was you could do it if n is greater than 4. Right. So notice that's a special case of this result. If n is 1, sorry, n is greater than or equal to 4. So if n is 1 and t is 0, we know that that's Nash equilibrium. You can implement a Nash equilibrium if n is greater than 3 or n is greater than or equal to 4. That's the Barney result. It's a special case of this result. So when I say, when we started doing this work, we realized that, these two literatures in the late 80s were proving sort of similar results. In the econ literature, you're getting results in implementing Nash Equilibria. You could do it if n is greater than 3, n is greater than or equal to 4. In the computer science literature, you were getting results saying that you could implement a mediator if n is greater than 3t. There was no k because there weren't rational agents in the computer science literature. And this can be viewed as a generalization of both results. But what was amazing to me is, again, these results were late 80s. We proved our first results on this, actually makes me feel old, in 2006. So there were like 17 years where these two literatures were going along in parallel. There were lots of results in the econ literature on implementing mediators, and tons of results in the computer science literature on multi-party computation, which can also be viewed as implementing mediators. And these two communities were going on in blissful ignorance of each other. And I stress, this was not, some obscure computer scientist in upper North Dakota working on this stuff. The computer scientists working on this stuff were Turing Award winners. And the economists working on this stuff were Nobel Prize winners. So this was quite prominent literature in both economics and computer science. But despite the crosstalk between economics and computer science, at least the communities working on this stuff were just not aware of what was going on. So here, our result implies the econ result, but we can do more. In economics, Elchanan Ben Porat introduced this idea of a punishment strategy. And roughly speaking, a punishment strategy says, well, if I catch you deviating, I can do something that will make you feel bad. Feel bad in this case means I can do something that will give you a payoff lower than you would have had you followed the protocol, right? So you might be tempted to deviate, and there's a chance you'll get away with it. But if I catch you, I can punish you. Right, and punish literally is a strategy that gives you a worse payoff than you would have had you not deviated. And we were able to show if 2k plus 3t is less than n, and there's a punishment strategy, we can implement the mediator. But the protocol is randomized, and we showed it has to be randomized. You can't use a deterministic protocol. So it has finite expected running time. What you're randomizing over, let me stress, is the running time. So that there will be executions to the protocol that take arbitrarily long amounts of time. The expected running time is small. It's a small constant, like 7. But, a small probability you'll have to go on for a long time. I stress this because I'm going to come back and talk about bugs in the econ literature. So remember the fact that we proved that the protocol has to be randomized. So we also proved other results. If 2k plus 2t is less than n, and there's a broadcast channel, then you can implement a mediator with epsilon error. There's a small chance you won't be able to implement. So you have an approximately correct algorithm. If k plus t is less than n and one-way functions exist, If you don't know the cryptography literature, roughly speaking, a one-way function is a function that's easy to apply but hard to invert. But don't worry about it if you're not a cryptographer. And there's a punishment strategy, then you can implement the mediator with epsilon error, even if k plus t is less than n. The point here is that these are all standard assumptions in the CS literature. Things like broadcast channel and one-way functions existing, this comes up in all the crypto papers. Punishment strategy came up in the econ literature. So here we're sort of combining assumptions, quite standard assumptions, from the econ literature and the CS literature. So the key idea here, if I have time, I'll actually give you a bit more detail of the proof, but it'll depend on how many questions there are. But we're going to reduce the problem to secret sharing and multi-party computation. So these were upper bounds. These were things that were possible. And we have matching lower bounds. So we know, for example, if 3 times k plus t is greater than or equal to n, then there is a KT robust strategy using a mediator that can't be implemented without a mediator, without knowing the utilities, without a punishment strategy, and then bound to time. So all the results here that we had, all these nice properties, they couldn't be done. But I stress this is an existence result. I'm not saying that there are also KT robust strategies that can, with a mediator, that can be implemented, even if n is smaller than 3k plus 3t. But I know there exists one that can't. So this result says all strategies can be implemented if 3k plus t is less than n. This is saying there's at least one that can't be implemented if 3k plus t is greater than or equal to n. And that's the best I can do. And this is important, that if 2k plus 3t is greater than or equal to n, again, there's a KT robust strategy with a mediator that can't be implemented without a mediator, even if there's a punishment strategy and even if utilities are known. So it's just the matching lower bound. And we have similar matching lower bounds for C and D. And these lower bounds, in some cases, use techniques that were known from Byzantine agreements of bringing in ideas from the CS literature. Lower bounds in running time. If 2k plus 2t is greater than or equal to n, then there's a game that can't be implemented using a deterministic cheap talk strategy. I'm going to stress this result, and for all B, that there's a game that can't be implemented using cheap talk that has expected running time less than or equal to B. So the expected running time can be long. Let me skip C. Part of why I'm interested in this, do I have this in later slides? So yeah, that there are all sorts of results in the econ literature. So as I say, the work of Folge and Barani around 1990, I think it was actually 89, gives theorem 1a with k equals 1. They did the special case of Nash equilibrium. Work in secure multi-party computation, note the date here, 88, gives theorem 1a for all k and t. So I'm claiming, it's not totally obvious, but I'm claiming that the work of Folge and Barani, which was published in 89, was actually subsumed by this work that was published in 88, although it was completely independent, that proved the general result for all k and t using secure multi-party computation. That's how we proved theorem 1a. So using these known results that go back to 88, a bit of extra work, we could prove theorem 1a. So had the economists known about these computer science results back in 88, they would have been able to prove their result with those techniques and get a more general result. Ben Porat, he was the one who introduced sequential equilibrium. And he proved he was the one who introduced the notion of punishment strategy. And he proved, or claimed to prove, that you could get theorem 1b in the special case where k equals 1 and t equals 0. So again, this says if k equals 1 and t equals 0, if n is greater than 3, and you have a punishment strategy, you can implement a mediator. You can actually even get a sequential equilibrium. So unfortunately, theorem 3a, our lower bound result, shows that Ben Porat's algorithm has to be incorrect. Now, I know this without even looking into the details of Ben Porat's algorithm. I know this because Ben Porat's algorithm is a deterministic bounded algorithm. He says, step 1, you do this, step 2, you do that, step 5, you do this, and then you're done. Our lower bound says there is no such bounded algorithm. Your algorithm must randomize to get this result. It must randomize over running time. So yes, it's possible that the expected running time is 5, but there will be executions that take more than 5 steps. In Ben Porat's algorithm, all executions take exactly 5 steps. We know this can't be done. So we knew that Ben Porat's algorithm had to be wrong, and then after spending some time looking at the details of his algorithm, we found the bug. But the point is, we knew it was a non-trivial bug because any algorithm that, in the spirit of his algorithm, that took 5 steps and then stopped could not be correct. The algorithm had to randomize over running time. This followed from our lower bounds. Ben Porat published an erratum and had a very different style of algorithm to which our lower bound doesn't apply, but Yuval Hedder extended Ben Porat's result to all k and proved matching lower bounds. So again, this Yuval is an economist. So again, this is work in the econ literature, but now let me go back to one quite recent result. Up to now, I've been considering synchronous systems. The economics literature considers only synchronous systems. But those of you who are familiar with the computer science literature know that in computer science, we're actually very interested in asynchronous systems. In asynchronous systems, so in the synchronous systems, the assumption was players communicate with each other, and then somehow a magic bell rings and they all make a decision in the same round. Why should that happen? It turns out the protocols all have this property that, they talk, there's a period of communication, and communication ends after round 10, and then you make a decision. But I claim in the real world we have asynchrony, where asynchrony, I don't want to go through the formal model in the CS literature, but roughly speaking, we're all running at different rates relative to each other. So, I might be able to process steps, in 10 rounds, I can process 10 steps. For you, in 10 rounds, you're on a much slower processor, you can only do 1 step. So our relative rates are quite different. Communication is asynchronous. I send you a message, it can take an arbitrary number of rounds before you receive it, or perhaps you don't receive it at all. And my claim is in the real world, we have asynchrony. Markets are asynchronous. There isn't necessarily a global clock. You can have what we call partial synchrony, where we're not too far off from each other. There's a bound, so 5 minutes on my clock is going to be at most 7 minutes on your clock. With complete asynchrony, there's no bounds at all, right? And in computer science, there are many systems of interest that are completely asynchronous. We can debate, if you've got global markets, how much synchrony do we really have? We certainly don't have exact synchrony. Clocks don't all run at the same rate. Maybe partial synchrony is a reasonable assumption. But my point is that considering purely synchronous systems is not necessarily a good modeling decision because you just are not capturing the real world, and particularly not capturing blockchain. So we in this case is Ivan Gefner, my student, and I, and we have a paper that's also joint with Daniel Lev and Itai Abraham. We asked what it meant to implement a mediator in asynchronous systems. Well, now there's some subtleties. Because in an asynchronous system, the typical assumption is that you have a scheduler. The scheduler decides who moves next. So it might be Hannah's turn to go next, and then Raphael's turn. And so it decides what order players move in, and it decides how long a message is going to take to arrive. What's the message delivery time of message? So we assume that the scheduler intuitively is an adversary that decides these things, and we want to show intuitively that no matter what the scheduler does, we can implement the mediator. But our notion... Somebody should turn off their... Our notion of implementation says that for every scheduler in the mediator game, there's a scheduler that implements the same outcome in the communication game and vice versa. So it's a quite strong notion of implementation. And this is just a subtlety that doesn't arise in the synchronous case, because in the synchronous case, there's a unique scheduler, and it says everybody's scheduled at every step, and messages take 1 round to arrive. And the result that we have is that if you can get a KT robust equilibrium with a mediator, then you can implement it using sheet talk if n is greater than 4 times k plus t. So we replace the 3 we had before by 4, and here we had the result before 2k plus 3t, now we have 3k plus 4t, again, increasing all the parameters by 1 if you have a punishment strategy. And then we have a matching lower bound as well. So I talked about some of this related work. There's a lot more related work in the CS literature. I mentioned that Urbano Villa, to Spanish economists, got theorem 1D, which talked about, just to go back, implementing a mediator if one-way functions exist and there's a punishment strategy. But we know that the Urbano Villa paper has to be incorrect because, again, they have a bounded protocol, and we have our theorem 3a shows there is no bounded protocol. So the lower bounds that we have from the CS literature actually show that so the Ben Poat result was published in JET, Journal of Economic Theory, which is a major journal. And I think the Urbano Villa paper was published in Econometrica. So again, these are major journals that took these results, but they are unfortunately wrong and not easily correctable. Because results that, if their protocol has the property, which it does, that it's bounded, that, we do step 1, 2, 3, 4, 5, and then we're done. Our lower bound results says there is no bounded protocol. So it's not going to be a small change to these protocols that's going to make them correct. The theorems are correct, but the particular protocols are not, and no easy fix is going to make them correct. So let me conclude, and hopefully leave some time for questions, that issues of coalitions and fault tolerance, I claim, are critical in distributed computing, but I sort of find it surprising that game theory never considered coalitions and fault tolerance in a serious way, because I would think that for, certainly in the Bitcoin world, but in lots of other applications of game theory in economics, robustness is actually really important. You want to allow for the possibility that, instead of assuming that everybody's rational, especially in these days of behavioral economics that casts, into doubt the assumption everybody's rational. So here is a way of sort of, if you like, an intermediate point between behavioral economics and classical economics, where we assume that most people are rational, but the robustness result says, okay, we can tolerate up to T irrational people. And actually, in this case, we don't care how they're irrational. Behavioral economics might give us some insight into maybe restricting the behavior of irrational players. But my claim is by combining ideas from all three areas, we can gain new insights for all three areas and prove interesting new results. So implications for distributed computing and cryptographies, we should consider rational players as well as Byzantine players. I think at this point, this is well understood. When we first wrote the paper, it was perhaps not as well understood. That one thing that this was an idea introduced by Lorenzo Alvisi, a colleague of mine at Cornell, that we looked at players who are malicious, who are bad, who will do anything. But in real life, you might also want to consider, Lorenzo called them altruistic players. I think maybe a better word might be obedient. Players who are willing to follow instructions, perhaps provided they don't get hurt too badly. In other words, I'm going to suggest a protocol that you should use. And, don't send your job to the printer if it's too big. And maybe you'll gain by deviating. But you might say, well, look, as long as everybody else is being nice, I'll be nice too. The world works better if everybody's nice. Being nice is not a Nash equilibrium. It's not, quote, rational. But in fact, in the real world, people are willing to be nice. Sometimes I would add the right, provided they don't feel like they're being taken advantage of. And maybe our protocol and mechanism designers should take advantage of the willingness of at least some people to be nice, to follow the protocol. Implications for game theory is that equilibrium notions should be more robust and maybe, again, take fault tolerance into account, but maybe take niceness into account. Cryptographic techniques can be helpful in achieving equilibrium. Other ideas from distributed computing that might be relevant, we might consider resource-bounded agents. I know Raphael has done a lot of work on that, and I've done some work with him as well, where we might say, maybe it's too hard to figure out what the equilibrium is. So what happens if we consider resource-bounded agents? Do we get different notions of equilibrium? And as I've tried to stress, that I think economics might really gain by looking at asynchronous systems, because in the real world, there is a lot of asynchrony in the Bitcoin world for sure. Let me actually stop. I have 2 slides on the idea of the protocol, but I want to allow some time for questions. So, questions?
So first of all, let's maybe thanks Joe, and then we'll take some questions. Okay, so we have a few questions in the chat. Maybe the people who are asking them want to read them, or so maybe Lu Yao Zhang has a question about the core. Do you want to read it yourself, or should I read it?
Actually, I'll go back to.
Okay, she's not, or he's not.
Yeah, I was just wondering whether you. Sorry.
Yeah, go ahead.
Yeah, there are two questions.
Okay.
One question is about the core, because in the core, people consider about coalition. Definitely, it's for non-cooperation equilibrium,
right? So
and
I
then
think
they do not have. Yeah. So I just want to know your thoughts on that.
I actually haven't thought about that. It's a good question. That we take the core to be sort of a notion that comes up more in cooperative game theory, and I was focused on not cooperative game theory, but it would be interesting to sort of take these ideas and apply them to cooperative game theory. I don't have anything sensible to say, but it seems to me a very reasonable question. So what can I say? Great question. What does this say about the core and more generally about cooperative game theory? That seems to be actually a really interesting research direction. And you said you had a second question.
Yeah, the second question is in Ariel Rubinstein's email game, he actually considered message loss, which in the chat I see another scholar says it's kind of like considered not as message delay, but message loss. So I'm thinking of message loss is like an infinite times a message delay. So maybe it's something like in the econ literature, we have the two extremes, infinite message delay or no message delay, but we don't have the middle way. So I sent the literature in the chat as well. It's some work by Ariel Rubinstein published on American Economic Review.
So I'm very familiar with Ariel's paper. He was trying to make a point about lack of continuity of common knowledge. So he was taking a rather stylized game where you send a message and I respond to you, you respond to me. It goes back and forth, and either goes back and forth infinitely many times or stops after a finite number of times. I think Ariel would agree. I don't think he was taking this as a realistic model of what happens in the world. His paper was more focused on various continuity properties of common knowledge. It's a beautiful paper, but I don't think that we would want to take seriously the kind of communication model that Ariel was proposing. I think economists need to look much more seriously at the general problem of communication, how long messages take to arrive, and asynchronous systems, and see what impact that has on many of the standard algorithms they consider. I mean, certainly in the computer science literature, we know there's a big difference in the kinds of results you can get in synchronous and asynchronous systems. It would be sort of surprising if there wasn't some kind of an effect in asynchrony in the game theory literature. And it might be interesting to see, well, if you can do something in a synchronous setting, what do you have, can you do it in an asynchronous setting? What do you have to give up? So let me stop there because I see there's lots of questions. So
now we have a question by Harald Ulik.
Yeah, I mean, wonderful talk. I learned a lot. I mean, as an outsider to this game theory, one question that I had was about the definition of strategy. I think you, if I may say, everything was very clear, but that one was sort of skipped a little bit, I suspect, because in the interest of time and because it's complicated. But if you think about, extensive strategies and what it can condition on and whether it can coordinate with others, and is there a difference between computer science and economics, and how important is to be,
I would say no, that I think essentially what, I'll tell you the formal definition in a second, but what computer scientists call a protocol and what game theorists call a strategy are essentially the same thing. Now, the formal definition, if you have an extensive form game, so if you think of a game tree, you've probably seen those. And in a game tree, they have these ellipses, which are meant to indicate you can't tell these nodes apart. You have the same information in both. Formally, a strategy is a function from these ellipses, these information sets, to an action. But you can identify an information set with local information. And if I think of a protocol as being a function from local information to actions, or a function from your local state to actions, I really think that the game theoretic notion of strategy and the computer science notion of protocol are really the same thing. But for the purpose of this talk, just think of a strategy as telling you what to do in all circumstances, as a protocol does as well. So, I mean, do I pick
next
time? Or are you going to pick?
No, yeah, Jacob, let's know.
Hey, Jacob.
Hi, Joe. That was a wonderful talk. I really enjoyed it. Thank you. I'm wondering about the asynchronous case. Why don't you get FLP impossibility style result?
In this case, because we're assuming, I mean, the answer is yes, you would get them, but that's not the question I'm asking. I'm asking if you can do it with a mediator, can you do it without? So that you don't get the FLP result if we already know you can do it with a mediator, and we're just trying to implement the mediator. So I should explain for people who are mystified by the question. FLP is Fisher-Lynch-Patterson, and they show that you can't do Byzantine Agreement even if there's only crash failures and even if t is equal to 1 in an asynchronous setting. So there's a huge difference between the synchronous setting and the asynchronous setting. But again, I stress that's not the result that we're proving. We're saying if you can do this, then you can do that. And what can I say? That FLP techniques don't apply to if you can do it with a mediator in the asynchronous setting. Yes, you can do it without a mediator in the asynchronous setting if n is large enough. But we're not saying anything about whether or not you can do it unconditionally without a mediator. That would be the FLP setting. Does that help?
Yeah, thank you.
We next have a question by Vincent.
Yes, thank you very much for the talk, Joe. It was really insightful. I had a question maybe that relates to some of the answers that you've provided. You provided bounds for asynchronous setting, synchronous setting, but there is a common view that the partially synchronous model is also very interesting for blockchain technologies. So do you see any open questions in this middle ground where you can solve consensus between synchrony? I
haven't thought about it really hard. My guess is that it'll be more like the synchronous setting, that the bounds that we get for partial synchrony will be the same as the bounds for the synchronous setting, although I haven't proved it, so take that with a grain of salt. But I think there are more general, I mean, we focused on certain properties of robustness and fault tolerance and coalitions. But I think there's many other questions you might want to ask. I mean, again, think about Bitcoin blockchain. Like, how long does it take to do these things? What are you giving up by if you take partial synchrony and say, as a function of the, how far apart we can be, how do things work out? How does this affect equilibria? So, I mean, I think there are a lot of questions that, we focused on one particular question, which was implementing a mediator. But why is that the only question of interest? I mean, surely not the only question of interest. So what can you, I mean, I'd have to think, but if you look at the application in the Bitcoin blockchain world, if you think about this game theoretically and what are the right questions to ask? I mean, certainly people are asking lots of questions about can you set the incentives up right to do certain things? So there's lots of game theoretic questions, and how are those questions affected by issues of synchrony and asynchrony in the in the blockchain world? So I should start, we looked at one particular question, which was implementing a mediator. It was nice because it related to stuff that had been done in the econ literature and the CS literature even back in the late 80s. I think it's an interesting question, but I don't want to suggest this is the only question anybody could ever ask. So, but I also, what is the right question to ask? Well, I think that's very much domain dependent. What are the effects of computational limitations in all these questions? That's a question I find really interesting. And I've done some of that with Raphael, but I think there's lots of other questions you could ask.
At this point, I think we should thank Joe, and I see there's a bunch of other questions out there. Maybe you want to just contact Joe.
Yeah, so